Hey guys, and welcome to lecture 3 of the Matlab course. I'm your lecturer, Satya, and first of all, thanks for being a part of this course. Thanks for attending the lectures and cooperating so far. So, in the previous week, we saw things like what matrices are, what the mathematical part of technicality of matrices was, and how to go forward with declaring matrices in Octave and Matlab and so on. So in this video, we'll further be extending our knowledge on the subject of matrices. We'll be looking at how to, use inbuilt functions to operate upon these matrices. We'll also be looking at how to print these matrices and vectors using some functions that we've already learned. We'll be learning about the practical implications of some of these functions and things that we're going to learn. We'll also further be learning about ways of initializing these matrices and vectors. And well, we'll also be learning about how to index and slice them. So without any further ado, I hope we can get into the subject. So if there are any questions or concerns, or if you're not able to see anything during the course of this lecture, um, please let me know in the MATLAB questions channel on the Discord. I'll always be there to help. So that being said, let's move on. So let me get started by freshly declaring two matrices. Let's say, all right, so first I'm going on and declaring this matrix A, which has a dimension of 3 by 2. And now the first function that we'll be dealing with to operate upon matrices is the size function. And what the size function does is that it returns the number of rows and columns of a matrix. So what I'm going to do is I'm going to have two variables m and n in a matrix that is going to represent the rows and the columns respectively is equal to size of A. And as you see, I'm assigned the values of the respective rows, number of rows and number of columns in A to the values m and n. So however, let's say we want only one of these. Let's say we want only m or only n. We don't need to necessarily do this kind of a declaration. All I need to do is I'm going to write m is equal to size of A, comma 1, and I'll be getting 3. Or let's say I need n is equal to size of A, comma 2, then well, I'll be getting that as well. So that is how you use the size function. Now there is one more function you need to know regards to size. At this stage, I'm just, it's a mathematical convention. It's not a computing convention, but I'm just using it so that, you get more mathematically inclined to the idea. So anyways, yes, it is highly suggestive that when you write code in a more formal way, in a more professional way, you give more descriptive names. But here, just remember that, I'll be using some mathematically conventional names when I'm doing declarations, just to maintain the mathematical clarity. Anyways, proceeding over there, our next function is the length function. So let's say I have length of A, then it's gonna give me the value 3. So what this means is that the length returns the value of the longest dimension. So let's say A is a 3 by 2 matrix and 3 is the longer one. So length is going to return size of the number of rows over there. So the thing is, in general, we don't use length a lot for matrices. We just go with the size function. But in the case of vectors, we generally like to refer to it as length as a more convenient way. So just another thing to know. So with this, the dimension returning functions are over. Let's move on to some more operative functions. So the first one we'll be seeing here is the sum function. All right, so sum of a comma 1, and let's see what this returns. So this is returning the sum of the individual columns of a matrix, all right? Or we call it sum along the rows. So the value of each row over there is being summed up to give the sum of that one particular column. So sum of column 1 is 266 and sum of column 2 is 175. So yep, and as you might have already gained an intuition, if we need the sum of the along the rows, then I mean sum of the rows, then we're gonna give sum of a comma 2, which will be as you see 44, 7, 77, 320, which are the sums of the individual rows, or we can also call it sum along the columns in a way. So be clear with that terminology. Just understand that, I mean, just get which the if the second parameter which you're passing is one, I mean the second argument you're passing is 1, then it's going to give you the individual sums of the columns, and if you're going to give the second parameter as 2, then it's going to give you the sums of the rows. So yep, just the way we have sum, we also have product. So the function for product is prod of a comma 1. So let's see what that returns. It's going to return the product. And very similarly, we can also do prod of a comma 2. And well, as you see, that will be along the the product of the elements of the rows. So at this point, I'd like to ask if there are any questions regarding these functions before moving further. I'd like to pause for a minute. If you do have any questions, please do let me know in the forums. All right, well, there seems to be no doubts about this, so, well, I'll be proceeding. For the next few set of functions that I'll be dealing with, I need particularly to deal with square matrices. So in case you're wondering what a square matrix is, it's just that m and n, the dimensions, the number of rows and columns are the same. So let me go ahead and get a 3 by 3 matrix for our purpose. All right, so I've declared a 3 by 3 matrix B. So the first function that I'll be talking about is the determinant function. So in the previous class, you would have learned it that the determinant is a certain number, a unique number that's associated with each and every matrix. Well, you would have some of you might have taken a linear algebra course and you might know more in detail about determinants, or please do refer to the rough outline that I've given to you about the concept of a determinant in the previous video. That being said, let me show you how this particular function works. So if I say, oh wait, I'm sorry, it's determinant B because A isn't, you see, so A here is a 3 by 2 matrix, and when I try to give determinant of A, it says that A must be a square matrix. So let's move on and see what it does to determinant of B. Well, there you go. So we see that the determinant is 3, 1, 1, 2, 6, 7. Yep. So the next particular function that we'll be dealing with is the adjoint of a matrix. So I think I've already told you in the previous lecture that the adjoint is a matrix of the cofactors of the individual elements. Well, anyways. Let's see how this works. Oh, I'm sorry. You see, I mean, again, I used A and it isn't working. So if I give it for B, wait, what's the error here? All right, wait, adjoint is supposed to work. I think I didn't add the library. I'll just look into what I made there. In the meantime, I'll just deal with inverse here in the second. So inverse of A, inverse of B. So I think I've already told you that, the inverse is something like, the reciprocal of, yeah, it's something like the reciprocal of a matrix. Well, I mean, that isn't very technical of a definition, but, just helps you, understand the concept. Um, yep, I hope that gives you an intuition. Now, one thing we need to understand about these is that the inverse of a function exists only if there is going to be a determinant. If the determinant is non-zero. I'm sorry, I got that term wrong. Okay, if the determinant is wrong, then if the determinant is zero, then it works. So it doesn't work. And if the determinant is non-zero, then we have an inverse. And this technicality in linear algebra is particularly known as singularity. So you know um, if a matrix has an inverse, then it has to be non-singular. In other words, the determinant shouldn't be zero. But however, octave is a precise language, and for that purpose we need to understand that even if the determinant is almost close to zero, if it's not zero, we still will be able to extract a result out of it. Let me just show you how that's actually done. So yep, all right. So we use a function called pinv for this particular operation. So pinv of b. All right. So well, if you see, you'll be able to understand that both inv and pinv here are gonna be having the same values, but in case b is a singular matrix, then the pseudo inverse is what you'll be using. So due to its factor of precision, it will be doing this. At this juncture, I'd like to add that the adjoint function actually doesn't exist. I apologize for the error over there. So I actually thought so. To actually compute the adjoint, we need to go by certain mathematical ways. So I'll tell you how that particularly works. The thing is that in matrices, the reciprocal of the determinant into the adjoint actually gives you the inverse. So what we'll be doing to get the adjoint of a matrix is that we'll be taking the determinant of A, and then we'll be scalar multiplying it with the inverse of A. And I'm sorry I used A because A is not a square matrix. B is the square matrix. So I'll use the square matrix here. And let's see what happens. So this is the value of our adjoint. Once again, I apologize for the error. The adjoint doesn't have an inbuilt function in Octave, but if you ever need to compute the adjoint of a matrix, understand that this will be the way that you have to do it. You have to just give it as determinant of B into scalar multiplied by inverse of B in that sense. All right, moving on. So yeah, the next function we'll be dealing with is the max function. So let me show you an implementation of this, and then we'll move forward. So val and ind. So value is the value of the maximum, and ind is the index of the in fact, let me just give that more in detail. Value and index. So value and index is equal to max of B. So what's going to be happening? So the values are 90, 101, and 91. And if you observe the matrix, you'll be understanding that this is the maximum of each column in specific, and the index where it is present in that particular column. So that is how you do it column wise. To do it row wise, there is a certain intricacy. Before going into that intricacy, let me just tell you that you need not necessarily give this index parameter. It's actually optional. If you need the index of the position where the maximum value is, then you use that, but if not, you don't need to give that. So let me show you an implementation where we don't use the index. So let's say value is equal to max of b comma, let me give a set of brackets here, and 2, and that gives me the value of the maximums along the rows. Now you might be wondering, in the previous functions we did not have this bracket in the middle, and now why are we doing this when it comes to a maximum function? This is because of a particular property of how the maximum function is defined in Octave, is that there is this intermediate parameter where we compare the values in matrix B with a set of values in another matrix to see which is the greater one, and thereby we use that to display results. It's something like it also acts as a comparing operator. So just to give the just to avoid a conflict in the parameters of the maximum function, we give that matrix as null, and then we proceed to give whether we want it along the rows or columns. So if you're going to ever use this notation, remember that the max function is unique here. Well, similarly, we also have the minimum function. Let me just show you an implementation of how that works. Min of b comma, let's do it along the columns this time. Okay, yep. So the values are 23, 23, and 2. So yep, that's how it works. So those are the maximum and minimum functions that we just saw. The next function we'll be dealing with is mean. So let's say mean is the arithmetic mean in this case, or as you say, the average of a certain set of values. So let me just denote it by average, and let's say I need the average of b along the columns. Then here we go. I'm gonna get the mean of values, arithmetic mean of values along the columns, as you see. And if I want it along the rows, I'll just give it as the second argument as 2. And that's how it works. So we also have the variance function. So let's say I need the variance along the we use the function var for here, variance of b along 2. Then all right, okay, so there is a mathematical conflict, I guess. So the normalization operator must be 0 or 1. All right, so that means that we're gonna have to do it using the brackets, I guess. Yep, let me just come back there. So usually that let me check. Just a second, because that is a mathematical error, and usually we don't get that. Yep. Anyways, let me try for variance is equal to var of b comma 2. I'm sorry, b comma 1. And yeah, all right, so this something here is related to some mathematical properties of the variance. So I haven't mathematically dealt with variance yet in this particular lecture. I mean, sorry, in this particular course. So you know what? I'll just leave variance to those of you who have done statistics. But just understand that variance, that the variance for a particular set of values can be given in this way. All right. So moving on, um, let's actually deal with something more graphical, and that is going to be with a histogram. So what a histogram is that it's a certain type of plot of the values, and well, let's actually declare a vector x for which we'll be doing this histogram plot. Let me just quickly declare a vector. Let's say, let me just put in some values here. 23, let's see, 78, 34 should be enough. And let me give it as histogram of X with, let's say we have a certain number of bins. So I don't know whether you're familiar with this terminology, but for a histogram, you need something called bins. Again, I'm not delving very deeper into statistics, but if you have during the course of learning ever taken a statistics course, you would know what a bin means. So in that case, you might find this parameter, this argument useful. So let's see what it returns. So it returns a histogram plot for my for the values in the vector x. Let me see what it does if I don't give a parameter. So let me go open the figure. Where's my figure? Yes. So it sees that, it's taking the default bin to be 50. I'm sorry. It's taking the default to be 10. In the previous one I declared it to be 50, but if you don't give that argument, it will be defaulted to 10. So I'm sorry for the small confusion that I created there. So remember, by default, it's 10, and you can always change the number of bins according to your wish. So anyways, the next operator we're going to be seeing is the transpose operator. I think you've already been told what a transpose is in the previous lecture, so I'll go straight to it. It's not very much complicated to use a transpose in Octave. You just give it as a dash. Let me actually tell you a small implementational trick here. In Octave, if I give a space dash, it's still gonna give me this. But in Matlab, if you're gonna give a space between a and the dash, it won't work. So just for the sake of, some of you might love to, code with a lot of spacing to make it look, more aesthetic. In this particular case of transpose, don't do that in Matlab. It's going to result in an error. So just for a clarification there. So let's deal with one final function before going on to the other sections of this lecture. So let's say I want to compare the values in a matrix with a certain other value, and return the indexes where my condition is satisfied. So let's say row and column are the indexes of a condition. Let's say find a greater than or equal to 7. So wherever the values of a are greater than, let's say not 7, let's give some other value like 20. So wherever the values are greater than 20, in those places the row and column indexes will be returned to us. And let's see, that's what we've got. We've got all the indexes for which the row and the column are for the values where the value of the element is greater than 20. So yep, that brings us to a conclusion of the functions which are used specifically for the purpose of matrices. The other functions like let's say log a, exponential of a, sine they all these functions which you use on normal numbers can also be used on matrices and vectors. They'll only be operating element wise, so that's just something to be kept in mind. So yes, let's move on to the in fact, before moving on to the next section, I'm just gonna pause and I'm gonna ask if there are any questions or clarifications with regards to this particular topic. So do let me know on the Matlab questions channel if there are any. I'll be checking it for a minute before moving on further. All right, sounds like there are none. Well, okay. Um, Now we're going to be moving to the concept of printing matrices and vectors. So you might have remembered in the first lecture I told you that there are two functions that we're going to be dealing with for input and output. One is the C-style fprintf and the other is the display function. So the display function is relatively easy here. All I got to do is I got to type display b, and here we go. It's going to display the whole matrix for me. But with the fprintf, it's not as easy. So let me just do a very normal fprintf statement and show you what I'm talking about. Let's say I do a formatting and I give a escape sequence /n and I give the matrix I want to print, B. All right, well, that wasn't the output we were expecting, right? It's basically printing all the values in a single line. So that's not what we want. So here's a deal with the the fprintf function. So what happens is that when you give only one formatter %f here, it kind of turns into a loop where fprintf goes through every single value or every single element and then prints it individually. So in that case, we need to particularly remember that it's going column wise. So you see here that it's printing 34, 90, 23, 23 again, 101, 78, 91, 56, and 2. It's going column by column. So here's a knack of how to get the fprintf to print our matrix as it is. So just concentrate closely on what I'm currently doing here. All right. So I'm giving you 3%fs, 3%fs, and the line feed. And here I'm going to be giving not B, but B transpose. And now look at the magic. It's printing us the matrix just as we want it. So what's the deal here? We know that it's going to be trying to print it along the lines, and that for every iteration, it will be meeting the escape sequence once. So what we're going to do is that if it's going to say that I'm going to be printing it column wise, we're going to change the rows to our columns. So basically, the row becomes a column, and well, the fprintf prints the first column while technically it's printing our first row, and then it encounters the escape sequence for the next line. It goes to the next line, and by the time the value will be 90, it will start going for the next row. So well, you might have a question over here that does this mean that I'm gonna have to give as much as %fs as the number of rows? Well, sadly, yes, and that is why the fprintf function is not exactly the best way to actually display a matrix. Well, it still works perfectly well for vectors because, you know, anyways, you see for a vector, it's just printing it along the row or the column. So, you know, it's just only one row or column. But when the number of rows or columns increases, then yes, fprintf actually becomes a headache. So yep, that was us seeing using how the disp and the fprintf functions work. So at this point, are there any questions related to printing these functions? All right, there seems to be no questions. So yeah, moving on, we'll now be talking about indexing and slicing matrices and vectors. If you'd seen the previous video, you'd remember that there was a particular way in which we saw how to access a particular element of a matrix. And how we did this was by giving the index of a matrix in brackets, in round brackets. And so it gives us the value at row number 2 and column number 2. And that's how this works. And in the case of a vector, it's very easy. You need to just give one parameter. Let me say x4. It'll give me the value at 4. So that is how you index it. I talked about it in the previous video itself. It's quite an easy concept. The only thing you need to actually keep in mind is that indexing starts with 1. So you go with 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. That's the order of how you'll be seeing it when you do indexing. So yep. So what is slicing? So what I mean by slicing is that I'm taking a particular part, or I'm kind of rearranging, or I'm changing the way elements are, or just taking a certain chunk of elements from a particular matrix. The first slicing operator I'm going to show is the colon operator. So what the colon operator is going to indicate is that you're going to take all the elements um, and just make them into one single vector. All right, so all the elements in A are just made into one single column vector. But however, that's not the complete purpose of the colon operator. So let's say I want all the elements of the second row. So what I'll be doing is, I know that it's a second row, but how do I show it that it's gonna be all the rows, I'm sorry, all the columns? I just give a colon operator there. So I think that gives you an intuition about the two ways the colon operator can be used. Number one is, of course, to show that we want the whole matrix converted into a single vector. And the second way, of course, is to show that we need all the elements of a certain row, or all the columns, all the columns of a certain row, or all the rows of a certain column. Either way, let me show you how we do the all the rows of a certain column here. So let me say A3, colon, comma 2. Then we have the elements of the second column, right? So I hope you got an intuition of how that kind of slicing works. So let me show you one more thing we can do here. Let me say B, comma 3, and the next argument being, sorry. So basically what I am telling here is that I want rows 1 and 3, and I want all the columns associated with both those rows. And what do we get? We get both those rows. So that is another way of slicing a matrix. You can use the colon operator to give a certain range, as we saw in vectors. So when you use the colon operators in that way, that's how it will be interpreted by Octave. So let's say I want, elements in rows 1 to 2. I'm just giving it as 1 to 2, and the columns of 2 to 3. What is it going to be doing? It's going to be giving the all the elements in rows 1 to 2, and the respective columns in 2 to 3. So when you use the colon operator as the range specifier, as we saw in the previous lecture, it'll be just using it as it is. But if you're gonna give just the colon operator, as we saw in the previous examples, it will be interpreted as all, or everything, or all rows, or all columns. So that's how it's actually interpreted. So yep, that's it with indexing. So now I'll be waiting for a moment, and I'll be seeing if there are any questions with related to indexing, or all these relevant things that I just talked about now. All right. So now that we're done with the various operations that we can perform about these matrices and vectors, let's actually go to some unique functions that help us initialize matrices and vectors, and these prove very, very useful, particularly when we're dealing with several things in MATLAB and Octave. They simplify our job a lot. So what are these? Um, so the first way of actually learning to build and initialize matrices and vectors is using inbuilt functions. So let me give you some of these functions. Let me just list them out for you to see what they are. So first one is identity. So, well, MATLAB and Octave have a pretty weird way of referring to the identity, which is I, as in the human body part. So that's I of, let's say I need an identity matrix of dimension 4 by 4. It's been noted that an identity matrix is always a square matrix, so it specifies it as a diagonal matrix where the elements on the diagonal are 1. So that's the identity matrix for all. Let's say I want a matrix full of ones, and that's going to be ones matrix. So I just use the term ones, and I get a 3 by 4 ones matrix. And then let's say I want zeros in a matrix. Um, let's say I want a 2 by 3 matrix, and I get a 2 by 3 matrix full of zeros. So those are some ways of initializing um, these matrices. Now let's also see one more way of doing things. Random, 1, 3. So let's say I want a 1 by 3 random matrix, which means that just a set of random values. Then it'll give me a set of random floating points in a matrix. We can also take random numbers drawn from a normal distribution and use them. Let's say a 1 by 4 matrix of that. So it's just that these values are taken from a normal distribution. Well, in the first one, that's not the case. So yep. So let's move on to the two very important functions that we use for vectors. So the first one is something called linspace, or line space actually. Um, that's how I'd pronounce it. So the line space is something like it's getting a number of elements that are evenly spaced between two numbers. So the first argument is going to be the first number, the second argument will be the second number, and the third will be the number of evenly spaced elements that we need in between them. So let's say I need 10 evenly spaced elements between 1 and 100. There we go. So these are the evenly spaced elements that we get. So these are to be remembered that these are linearly spaced. If we need them to be logarithmically spaced, then we just give it as log space. Let's say 1 to 100 with 10 elements. Then we're gonna get logarithmically spaced elements there. So we're gonna get 10 logarithmically spaced elements in that space. So those are two very important things to remember with regards to initializing vectors. So now that I've actually talked about all these methods, let me just actually go through a run through of them. We talked about the identity, ones, zeros, line space, log space, and of course random. Where do we use all these? So well, the identity function, obviously, as you know, has a lot to do with linear algebra and, various operations in linear algebra. And well, that's it. We don't use it for a lot of special purposes. However, the ones and the zeros functions can be used to initialize matrices which hold sums and products. So let's say that you're going to store some sums of certain elements in a particular matrix. Then you need to understand that these sums, there needs to be a certain value in place before we start adding those sums into those places, because otherwise they'll be just taking some random garbage values. So it's always good to just initialize that matrix which is going to hold the sums with zeros, and that is mainly why we use the zeros function a lot. Well, in the case of products, if you're gonna have a matrix store the product of certain elements, then well, you might get an intuition that you don't use zero in that place, because of course that will render the whole product to zero. You use one instead. So those are the main uses of the zeros and the ones functions. The random is used for a more special purpose. It's also used for initialization, but it's used for initialization in places where you need what is known as symmetry breaking. So symmetry breaking is this unique concept where in certain implementations of these matrices and vectors, all the elements cannot be the same, or there are certain conditions like that. In order to break those conventions, um, we actually just initialize them with random values. One of these typical examples is gradient descent, so where you actually do that. Well, of course, I mean, in more advanced technologies, what you actually do is you make more um, educated or specific choices for these random numbers. But in general, it's just good to know if you're doing in an implementation, the random function can be handy for initializing in places where you need symmetry breaking. So, yep, that is the primary use. So are there any questions with regards to the initializations that we just learned till now? Well, all right. Don't seem to be at the moment. So, yep. Well, it's good to say that we've actually finally come to the final part of today's lecture. That is using slices of a matrix or vector to build another vector. So let's say I want to edit out a matrix, all right? So we know that we have this A matrix 3 by 2, all right? Let's say I want to edit that matrix. So what I'll be doing is, let's say I want to um, edit the second column of A to B, um, 10, let's say 10, 11, and 12. Yeah, that will be doing. So yeah, you see that the values in that column have been changed. So by using this slicing operator, you can also change the values in a matrix or a vector. So that is something important to remember. Or you can also append. So let's see how that works. So A is equal to the matrix A itself, space 10, comma 11, comma 12. What does this lead us to? That is just appending that is just appending 10, 11, 12 along with A to give us this particular 3 by 3 matrix. So that's how appending actually works. So now that we've studied appending, um, let me go into two other ways of one more way of how this appending can be done in vectors. So let me have a vector x. All right, so in this vector, let's say we've learned about this particular way of using the colon operator for range, right? Let me say I want the values 1 to 6, and then I also need the values. Let's say, let me just put some value, let's say 29, 30, 31. So what is this going to do? We'll have all the elements 1 to 6 as the colon operator, and then it uses the values which you have given. So the range operator here just can't be used individually. We can also use it in these kinds of ways. So you can make use of these kinds of implementations to build your vectors and matrices. So before moving on to the next part, of using slices to build existing matrices and vectors. Let me just initialize two more matrices. Let's say I'll just initialize two. Let me just say ones 3 gamma 4. I'm sorry, 3 gamma 3 to make my job easier, and D as let's say rand gamma 3. So yep, I have two matrices. So let's say I want to build another matrix E using these two matrices, then that's all I'll be doing. I'll be doing C space D in E, and well, that's gonna append them side by side. So why is this? You understand that when you build a matrix, when you go declare a row, you just give a space in between or a comma in between. And that is kind of how the appending interprets too. So when you just say C space D, it says that, you know, it's kind of to be appended side by side. And the same way that when you move to a new column, you give a semicolon operator. If I'm going to give E is equal to C semicolon D, well then it's going to be appending them top and bottom. So well, yes, that summarizes and winds up our discussion of initializing matrices and vectors using slicing. So in this lecture, we went through some functions, and then we learned about printing, and then practical implications of where we'll actually be using these, and of course, you know, indexing and slicing and how they actually work. So, well, till this class, till the third lecture, I'd be saying that a lot of work that we did is concerned with computations and how to bring out the essential factors that lead us to computation. In the next lecture, we'll be learning more about how to actually build programs and achieve tasks. We'll be moving on to the step of moving forward from computation and using these computations to get powerful results and applying them to real world problems. In other words, I'm just talking about scripting here. And so yes, we'll be talking about scripting and how to manipulate statements and all these stuff. Well, before closing this lecture, I'd like to look for the forums for one final time to see if there are any doubts. I'll be only happy to clarify them. So, yep, anyways, thanks a lot for watching or attending this session. Hope you had a wonderful experience. If you have any feedback or have any questions, I'll always be there to help. You can always ping me on the Matlab questions channel or even privately. Well, yes, I do have homework for this session, and I'll be posting it in a while. So, yep, I'll keep you waiting until then. So, yep,